Hello and welcome back to ARTS. In this video, we'll be going over the big five kinematic equations and how to use them. So I won't be going over the derivations in this video because that could stretch it out longer than we need to, and some people aren't really interested in the derivations. But I do recommend you watch the other video I push out on that, because it's gonna help you understand more about where it came from, and then if you have that knowledge, you're likely to do better on a test than someone who just blindly memorized it. Okay? But yeah. And also these equations tie into kinematic projectile motion, and that also I won't be going over in this video. This is more of an introduction to these five equations, and projectile motion heavily uses them. So we'll be going over projectile motion later though, because that's a bigger topic and a bigger video. So let's get started. Here are your five equations, the big five of kinematics. Vf is equal to Vi plus At, the velocity time equation, which tells you if you had an initial velocity and if you're accelerating for a certain amount of time, what's your Vf going to be? And something I forgot to mention, but this wasn't really complicated enough to make it into the big five. This is more of the little one by itself, right? The position time equation we learned earlier. V average is equal to 1/2 Vi plus Vf. I won't go over why it's only for constant acceleration, but I mean, it's kind of understandable, right? If you had a velocity time graph that looked like a parabola, which doesn't have constant acceleration, because that acceleration graph would look like this, right? Keep changing. Then you understand how you can't really calculate the average because the change is different each time. But for a linear velocity graph, you could, which means the acceleration has to be constant. Hf is equal to Hψ plus 1/2 Vi plus Vft. This is the position time equation. And then Hf is equal to Hψ plus Vit plus 1/2 At squared. This is the position acceleration equation. This gives you, position if you don't have Vf. And this is the velocity displacement equation. So here you don't have a time. Vf squared is equal to Vi squared plus 2a Hf minus Hψ, or delta Hs. This is displacement, and you can also write these as delta Hs, right? This is just a more stylistic choice. So if I was to subtract Hψ from both sides here, I could do delta Hs is equal to the rest of the expression, right? And I could do the same thing here. But this is a more stylistic choice, and I feel like this one helps me more, so I keep it this way. Okay? And then, before we move on, you have to notice something. All of these equations are missing one variable, right? This one doesn't have x. This one doesn't have x or t. At least one variable they're missing. This one doesn't have acceleration. This one doesn't have velocity final. This one doesn't have time. And I'll tell you why that matters later on, okay? So if you were to go down, these are more derivation slides, which I'll be going over in my derivation video. I'm going to tell you the 4 steps that you need to solve any kinematics equation, okay, using the big 5. List every variable you have given plus the one you must find, okay? Then you list all the 6 kinematic variables, Xi, Xf, Vi, Vf, A, and T. Identify the one variable missing entirely from that list. Choose the equation that does not contain the missing variable, okay? Because oftentimes you're not going to be given all these variables. You'll be given some of the variables with some missing. So then you have to work your way and you have to find out how to get what you want, even without all the information. These big 5 are a consolidation of all the physics related to kinematics, right? So with these big 5 memorized, you can solve almost any kinematics equation, because even if one variable is missing, you know how to use these equations to get that. So for example, right, I'm going to give you an example question, which I'll walk through with you. A car starts at rest and accelerates at 4 meters per second squared for 5 seconds. First, I write all the variables I have. A is equal to 4 meters per second squared. T is equal to 5 seconds. Velocity initial is equal to 0 meters per second. Okay, why is that? Because if it starts at rest, that means you didn't have any velocity at the start, right? And then I list all the other variables. VF. So I have this. I don't have HF. I don't have HI. These are the variables I'm missing. So first, let me find VF. Because I can find VF using just these equations. So how would I find VF? I mean, just these variables. So use the kinematic equation. So you find out which kinematic equation you have to use, right? Which kinematic equation has all these terms and you can use it. Well, VF equals VI plus AT. VF is equal to 0 meters per second plus 4 meters per second squared times 5 seconds. Seconds cancel out. You're left with 20 meters per second, like you can see over here. Okay, and I'm going to erase this, but I'm going to keep the other stuff. So now I know VF, so I'm going to put VF up here because I know him. Right, I know VF, which is 20 meters per second. Now, if I wanted to find the displacement or delta x, which I do, right? Because I know HF and HI, but I don't know anything else. So I can actually do two equations. I can do this equation, or I could do this equation. So you have a lot of choice in kinematics. So here, you're going to use this one. But keep in reminder, this only works because HI is 0, because you start from rest, okay? See, in this case, you do know HI. HI is equal to 0 meters, and you start from rest. If you're assuming you're not starting at some, like, you put some x-axis and then you're moving away from that. So then, HF is equal to 0, because VI times T, VI initial is 0. So 0 times 5, I'll just write it down, but it doesn't really matter, right? 1/2 AT squared plus 1/2 acceleration, 4 meters per second squared. And time squared is 25 seconds squared. Okay? Which gives us, seconds squareds cancel out, 2 meters times 25, or 50 meters. Perfect. But if you didn't have HI or HF, then you would have to use this equation. Okay? And then this one I could just verify. It's not really just solving for it, but I could just verify. So in kinematics, you have a lot of choice, and you have a lot of missing variables as well. So you have to use which one is best suited to your situation. Which variables are missing, and which ones do you need to find? And which ones do you already have? And then manipulate those to get your answer. So let's go over some problems. Obviously, I have more in-depth problems later on, like I always do, on artslearning.com, and PDF and videos regarding those that I'll be going over. But for right now, let's try some quick problems, okay? Okay, I'm assuming you gave it a pause and you worked these questions out. So let's go over it now. Final velocity. So I know it's going to be VF. And there's two equations for that, right? VF squared is equal to VI squared plus 2A delta x. Or VF is equal to VI plus AT. I don't have delta x here, so I know this equation is not it. I'm going to cross it out. VF is equal to 4 meters per second plus AT, 2 meters per second squared, times 6 seconds. So VF is equal to 4 meters per second plus seconds cancel out. You're left 1 second in the denominator, 12 meters per second, or in other words, 16 meters per second. So let me erase all of this and keep the 16 meters per second over here. Okay. So HI is equal to 0. VI is equal to 8 meters per second. A is equal to negative 2 meters per second squared, and T is equal to 3 seconds. Find the displacement. So since HF minus HI is the displacement, or delta x, But SI is 0, right? So then we just replace this with this, and the displacement would just be SF. Because SF minus 0 is just SF. SF is equal to, which equation could I use? Well, this one. SI plus VI times T plus 1/2 AT squared. Because this one has all the variables I have. I'm missing velocity F, so I don't need velocity F here. I'm solving for SF, so I can use these equations. SF is equal to 0 meters plus VI times T, which is 8 meters per second times 3 seconds plus 1/2 negative 2 meters per second squared times T squared, or 9 seconds squared. This should give you SF is equal to 24 meters plus negative meter per second squared times 9 seconds squared. Second squares cancel out. The 2 and negative 1 makes 2 and negative 2 make a 1. Negative 1. You get negative 9 meters. So your final answer is, subtract this, 15 meters. So I'm just going to erase all this work here. But obviously you want to show your work, right? A lot of times you don't get credit if you don't show your work. So in this case I would write SF, but displacement is delta X, right? But since that SF minus SI, and we know SI is just 0, delta X is just delta SF. Okay, so we're missing T and we want to find the displacement. Which equation doesn't include T? Remember? If you do, it's this one. VF squared is equal to VI squared plus 2A delta X. So VF is equal to 15 meter per second squared is equal to VI squared, 5 meter per second squared, and plus 2A. 2 is 2 meter per second squared. So this is 2 meter per second squared, or this is 5 meter per second whole squared, times delta X, which is something we don't have, right? We're missing T, and we're trying to find delta X. Match this up. 225 meters squared per second squared minus 25 meters squared per second squared is equal to 4 meter per second squared times delta X. 200 meters squared per second squared times second squared per 4 meter. I just multiply by the inverse of this is equal to delta X. This cancels out. This is left with 50, and this is left with M. 50 meters is the displacement. Pretty neat. And really, once you get the hang of this stuff, it's pretty fun, dare I say. You're missing acceleration, and you want to find the displacement. So what's the equation that misses acceleration? This one. Yep, this one. I mean, they didn't tell you that it's constant acceleration, but let's assume it's constant acceleration, okay? Now, SF minus SI, that becomes the displacement. So displacement is delta X is equal to 1/2 times VI plus VF. VI is 2 meter per second plus 14 meter per second times T, or 4 seconds. Delta X is equal to, this becomes 16 meter per second, 8 meter per second times 4 seconds, or 32 meters. Right? So this is it's not that hard by itself, but when coupled with projectile motion, it could become a real pain. So right now, they might not seem that tough, but I promise you, they do get harder. And as always, if you want to see my derivations video, be sure to look at that. And if you want to see how they're used with projectile motion, as always, I'll be pushing out a video regarding that as well. And I'll have a comprehensive unit review on these equations and how to use them. But it's pretty simple, right? Find out which variable is missing, find out which one you need, and then use the equation that you need. And memorize all these 5 equations, because otherwise it's going to be pretty hard, because you're not going to be able to derive them on the spot. I mean, you could, but probably take you some time, no? Otherwise, have a good day, and next time we'll be going over synthesis and projectile motion.